This prevents total wheel slip. CSX transportation averages 0.32 adhesion on dry rails, enough to pull 25 cars. 4 diesel-electric locomotives at the front pull all of it, and they do this every single day across America without fail. So, here's the question. How does a locomotive weighing 200 tons pull 100 times its own weight without the wheels spinning out of control? You're about to find out exactly how this works. By the end of this video, you'll understand the physics and engineering that makes American freight railroads move 1.7 billion tons of goods every single year. Let's start with the most basic question. What actually makes a locomotive move forward? The answer comes down to one word: traction. Traction is the grip between the locomotive wheels and the steel rails underneath. This grip turns engine power into forward motion. Without traction, the wheels would just spin in place like a car stuck on ice. And here's where trains become interesting. They almost never slip, even when pulling insane amounts of weight. To understand why, we need to talk about Newton's third law. You probably learned this in school. For every action, there's an equal and opposite reaction. When a locomotive engine makes the wheels turn, the wheels push backward against the rail. The rail then pushes forward against the wheel with equal force. That forward push is called tractive effort. Engineers measure it in pounds of force in the United States. A modern freight locomotive like the EMD SD70 ACE can produce 18,000 pounds of tractive effort when starting from a dead stop. That's enough force to drag a 747 airplane across the ground. And locomotives use this force to start trains weighing 15,000 tons on flat ground. Now, here's the key. Tractive effort has a limit. That limit's called adhesion. Adhesion is the maximum friction you can get before the wheels start slipping. There's actually a formula for this. Maximum friction force equals the coefficient of friction multiplied by the normal force. The coefficient of friction is a number that tells you how grippy two surfaces are when they touch each other. For a steel wheel on a dry steel rail, this number sits between 0.25 and 0.40. When the rail gets wet or oily, it drops to 0.10 or 0.20. The normal force is simpler. It's just how much weight is pushing down on the driving wheels. A typical freight locomotive weighs about 400,000 pounds, which is around 200 tons. On a 6-axle locomotive, that weight spreads across multiple wheel sets. At a friction coefficient of 0.30, you get roughly 60,000 pounds of tractive force per truck. A locomotive has 2 trucks, so the total comes out to around 180,000 pounds of pulling power. And this is where steel wheels become amazing. You know how car tires are made of rubber? Rubber squishes and deforms when it touches the road. That deformation wastes energy as heat. Steel wheels on steel rails barely deform at all. The contact patch where the wheel touches the rail is tiny, about the size of a quarter. 1 square inch of contact, and that steel-on-steel contact creates almost zero wasted energy. The rolling resistance for train wheels is between 0.001 and 0.002. For truck tires on asphalt, it's 0.01 to 0.02. That's 10 times more resistance. So, more than 99% of the locomotive engine power goes directly into pulling the train. Trucks waste a lot of energy just fighting the road. Okay, so here's the big question everyone asks. If the locomotive only weighs 200 tons, how can it pull 20,000 tons? The train weighs 100 times more than the thing pulling it. Why does a locomotive not just slide backward? The answer is that train cars roll on their own wheels. They're not being dragged like a sled across the ground. Every freight car has its own axles and bearings that spin freely. The locomotive only has to overcome a few forces to get the train moving. First is rolling resistance in the car bearings. This is tiny, about 1 to 2 pounds of force per ton per mile. Second is air drag. This increases with speed, so it's almost nothing when the train starts from a stop. Third is grade resistance. Going uphill adds 20 pounds of force per ton for every 1% of slope. Fourth is curve resistance when the train goes around bends. For a 10,000-ton train sitting on a flat track, the total resistance at startup might only be 20,000 to 30,000 pounds of force. One locomotive can handle that easily with 180,000 pounds of tractive effort available. The freight cars don't pull backward against the locomotive. Their wheels just roll along, connected by couplers that pass the pulling force from car to car like links in a chain. This is why a small switching locomotive can push 50 cars around in a rail yard. Once the wheels start rolling, physics works in your favor. Momentum takes over and you don't need as much force to keep things moving. A 10,000-ton train rolling at 20 miles per hour has enormous kinetic energy stored up. The locomotive just has to overcome the small friction losses to maintain that speed. Starting is the hard part. Keeping things rolling is easy. Here's something else that helps. Adhesion actually increases when the locomotive starts pulling a heavy load. When you couple a heavy train to a locomotive, the pulling force creates a twisting motion in the locomotive truck. The coupler sits about 30 inches above the rail, while the axle is at rail level. Pulling forward puts a torque on the truck that shifts weight toward the rear driving wheels. This weight transfer increases the downward force on those wheels by 20 to 30%, and remember, more downward force means more adhesion. The formula for this weight transfer involves the coupler height above the axle and the wheelbase width. For 100,000 pounds of pulling force, you get an extra 25,000 pounds of downward pressure. Your grip increases right when you need it most. There's another trick at startup. When the locomotive jerks forward with controlled acceleration, tiny rough spots on the rail surface bite into the wheel. This temporarily spikes the friction coefficient up to 0.45 or higher. Engineers designed the system to take advantage of these physics. Let me give you a real example. Bnsf Railway runs coal trains from Montana power plants in Texas. A typical load is 120 hopper cars at 115 tons each. That comes out to 13,800 tons total. 3 SD70 ACE locomotives pulling together produce about 540,000 pounds of combined tractive effort. Their adhesion factor sits between 0.25 and 0.35. What happens when it rains and the rails get slippery? The locomotives carry sand hoppers on board. They drop sand right in front of the wheels to grit up the contact patch. This brings the friction coefficient back to 0.2 or better. The result is that trains move 470 tons of cargo per gallon of diesel fuel. Trucks only move about 20 tons per gallon. That's a massive efficiency advantage that saves money and reduces emissions. Now, let's talk about the engineering that makes all of this work in the real world. American freight locomotives are built heavy on purpose. More weight means more downward force on the wheels, which means better adhesion. A typical 6-axle freight unit weighs between 400,000 and 432,000 pounds. The Union Pacific Centennial Class DD40AX locomotives from the diesel era weighed 980,000 pounds with 8 axles. All that weight squeezed every bit of grip possible for hauling loads over the Rocky Mountains at 6,600 horsepower. Wheel design matters a lot too. Train wheels are flanged and conical, meaning they taper at a ratio of 1 to 40. This shape helps wheels self-center on curves and distributes the load evenly. The cone shape makes the heavier side ride a bit higher, keeping good contact with the rail. American railroads use 136 pound per yard continuous welded rail. This means the rail weighs 136 pounds for every 3 feet of length. The rails are welded together into long continuous sections instead of having gaps every few feet. This creates a smooth surface with low resistance and good friction when the rail is clean. The welding process happens on site using thermite reactions that generate extreme heat. Workers grind the joints smooth so there are no bumps to slow the train down. High plates and crushed rock ballast underneath keep everything stable, even under 286,000-pound freight cars. The 286,000-pound limit became the American standard in the 2000s. Locomotive truck design is crucial for adhesion. ACC truck configuration means all 6 axles are powered. This spreads the weight for 25% or better adhesion utilization. ABB configuration with only 4 powered axles gets around 20%. Modern trucks use high adhesion motors with slip detection systems. If one wheel starts spinning, computers shift power to the other wheels through inverters. This prevents total wheel slip. CSX transportation averages 0.32 adhesion on dry rails, enough to pull 18,000-ton intermodal trains over the grades in the Appalachian Mountains. Distributed power is another big advancement. Instead of putting all locomotives at the front, railroads place remote-controlled units in the middle of the train or at the rear. These add tractive effort exactly where it's needed, reduce stress on the couplers. A Union Pacific manifest freight might run in a 4-2-3 configuration. 4 locomotives up front, 2 in the middle, 3 at the rear. That adds up to over 30,000 horsepower for pulling 15,000-ton loads. Think of it like having multiple tractors in a convoy all working together through radio signals. Now, we need to talk about what happens under the hood. The power systems where diesel-electric locomotives really shine. Unlike a car where the engine connects to the wheels through a transmission, diesel-electrics use the engine as a generator. A 12 or 16-cylinder prime mover engine spins a main alternator at around 1,050 revolutions per minute. This produces between 600 and 1,200 volts of alternating current. Older locomotives use rectifiers to convert this to direct current for the traction motors. Modern units use inverters to create variable frequency alternating current. Either way, there's one traction motor for each axle, mounted right in the truck frame. Why use electricity as the middleman? Because it gives you incredible efficiency and control. The diesel engine runs at its peak torque producing speed regardless of how fast the train is going. In a car, you have to shift gears because the engine only makes good power in certain RPM ranges. Locomotives skip that problem entirely. Traction motors deliver over 100,000 pound-feet of torque when starting from a dead stop. As speed increases, torque decreases following a constant power curve. The formula is horsepower equals tractive effort times speed divided by 375. At 10 miles per hour, a 4,400 horsepower locomotive produces 165,000 pounds of tractive effort. At 50 miles per hour, it produces 33,000 pounds. And that's still enough to haul 10,000 tons at 60 miles per hour. The shift from direct current to alternating current motors changed everything in American railroading. Early diesels from the 1920s through the 1980s used DC series wound motors. These created high startup torque because current and torque have a squared relationship. But DC motors have brushes and commutators that wear out and sometimes catch fire. Alternating current traction arrived in the 1990s. General Electric released the AC 4400CW in 1993. EMD released the SD70 Mac around the same time. These locomotives use three-phase induction motors with IGBT inverters. AC motors have no brushes to wear out. They handle overloads better, up to 150% capacity during wheel slips. And they boost adhesion by 20 to 30% through precise torque control. The impact was huge. 3 AC traction locomotives can do the work that used to require 5 DC units on heavy coal trains. Bnsf brought 450 SD70 Mac locomotives and revolutionized their Powder River Basin coal operations. They cut locomotive needs by 40% overnight. Dynamic braking is the final piece of the puzzle. And going downhill, the traction motors reverse their function and become generators. They convert the train momentum back into electricity. This power feeds into grids on the locomotive roof where it turns into heat, or in newer designs, it charges batteries. On a 1% downgrade, dynamic braking recovers about 50% of the energy. This dramatically reduces wear on the air brakes. That matters when you're descending for 100 miles through mountain passes like the Cascades. Without dynamic braking, you would burn through brake shoes constantly. The heat buildup could warp wheels or even start fires. Dynamic braking solves all of that while making the locomotives more efficient overall. American railroads have been chasing pulling power since the very beginning. The 1869 Golden Spike connected the Transcontinental Railroad and launched an era of bigger and bigger steam locomotives. Union Pacific's Big Boy class from 1941 weighed 1.2 million pounds and produced 6,290 horsepower. They used cylinder pressure for tractive effort, generating 135,000 pounds of force at startup. Those 72-inch driving wheels and 540 pounds per square inch boiler pressure hauled 3,500 tons over mountain grades. But steam locomotives burned massive amounts of coal, needed water every few miles, and got stuck in snowdrifts. Diesel changed everything. The first diesel switching locomotive appeared in 1925. General Electric built a 300 horsepower box cab unit for New York City rail yards. It cost 50% less to operate than steam. The 1934 Burlington Zephyr proved that diesel could power passenger trains. Its 600 horsepower Winton diesel pulled 10 cars at 110 miles per hour. World War II shortages accelerated the switch to diesel. EMD's FT locomotive from 1939 produced 1,350 horsepower and toured 35 different railroads. After the war, orders flooded in and over 1,000 units were built. In 1960, steam was completely gone from American mainline railroads. Diesel locomotives cut train crews from 200 workers down to 5 and boosted ton miles by 300%. The AC traction era began in 1993 when Burlington Northern ordered SD-70 Mack locomotives. Today, Union Pacific runs 20,000-foot intermodal trains on the Sunset route with over 200 cars weighing 15,000 tons. BS-44 AC locomotives with exhaust gas recirculation meet Tier 4 emission standards while pulling freight across deserts without breaking a sweat. Let me give you some modern numbers that show what's possible. Union Pacific set a record in 2023 with a 13-locomotive, 18,000-ton intermodal train over Donner Pass. That one train replaced about 1,000 semi-trucks on the highway. Bnsf runs 16,800-foot trains on the Transcon route between Los Angeles and Chicago. 13 GE units pull 14,000 tons of containers. CSX hauls 12,000 tons of phosphate through Florida swamps using SD-70 ACE locomotives. Their adhesion holds at 0.28 even in that humidity. The heaviest train ever tested in the United States was Union Pacific's 1978 Tehachapi experiment. They connected 40 locomotives and pulled 25,000 tons. It was a publicity stunt, but it proved where the limits are. Routine operations today handle 7,000-ton coal unit trains with just 3 locomotives. AC traction adhesion above 0.40 makes this possible. Of course, there are challenges. A 3% grade like the famous Saluda line in North Carolina adds 60 pounds of force per ton of train weight. For a 100-ton car, that's 6,000 extra pounds of resistance. The solution's helper locomotives, or distributed power units pushing from behind. Slippery rails from fallen leaves in Appalachian autumn or morning dew require quick thinking. Wheel slide protection systems cut power within 10 milliseconds when slip is detected. Sanding systems add 20 pounds of extra grip per hopper load. Coupler strength limits how hard you can pull. The AAR Type E coupler maxes out at 750,000 pounds of force. Pull harder and cars start buckling. Throttle notches divide locomotive power into 8 steps so engineers can increase pull gradually. Computers blend the power across all locomotives automatically. Crew training simulators at the Transportation Technology Center teach engineers how to start heavy trains without wheel slip. Weather creates problems too. BNSF operates rotary snowplows to clear mountain drifts. Union Pacific sprays anti-icing solution to keep rails grippy in winter. Compared to other forms of transportation, rail dominates heavy hauling. Peterbilt semi-truck maxes out at 80,000 pounds gross weight. Its 500 horsepower engine produces about 50,000 pounds of tractive effort. The rubber tires slip at a friction coefficient around 0.7, and fuel efficiency drops to 6 miles per gallon. A single truck driver can only move about 20 tons of cargo. Meanwhile, one train crew of 2 people moves 10,000 tons or more. The productivity difference is staggering. Airplanes lift tons of cargo but cost $10,000 per hour to operate. A Ford F-350 pickup tows 35,000 pounds maximum under perfect conditions. Trains carry 20 tons per axle with basically unlimited length. The cost works out to about 1 cent per ton mile. The future brings even more pulling power. Wabtec's FLX drive hybrid battery electric locomotives add 2,000 horsepower burst during startup when you need maximum tractive effort. Union Pacific's testing hydrogen fuel cell locomotives for zero-emission operations. These could change how America moves freight in the next decade. BNSF runs autonomous train trials where artificial intelligence optimizes tractive effort by predicting adhesion from weather data. Precision scheduled railroading strategies at major carriers mean fewer trains running heavier loads. This pushes adhesion technology even harder than before.
Okay, if there's one AI site builder you need to meet, it's this dope tech from Wix. Now, this whole flow is a conversation.